Okay, so this was the last problem we were talking about, and there was this problem where we had two spheres that have a certain mass and they're separated. They have a certain charge. That means that there's an electrical force separating them, and they're joined by a string. And the problem mentioned that the string is insulated, and that's a concept we're going to be seeing further on. But when something is electrically insulated, it means that that particular material does not permit or does not allow a conduction of electrical energy. Okay, so if something is electrically insulated, it means that electrical energy can't be transmitted. Okay, and sometimes that's desirable because I want things to be electrically separated or isolated. And so this situation generates a balance. The two charges are the same, but we don't know the value of the charges, and that's what we're trying to find. Okay, so this was done by House Power Rangers, and you guys had a procedure there. I'm going to do a procedure here, and the slides are also actually going to have another procedure that's very similar to the one you guys did, just so you have different alternatives. And we talked about that last class, I believe. Viviana, paraphrasing, asked the question of which was the better way. As long as you're doing a complete procedure that has all the steps and you're following the rules, mathematical and physical, it's fine. It's not that one is better or one is worse. It's just that you're doing things differently. So that's at least the way I approach it. Okay, so I'm just going to go through this. So we've got the two spheres. I'm going to write down one of them here. Okay. I am the spheres are of the same value. I'm just writing it down blue. The nomenclature I'm using, if you notice, is that blue is negative and red is positive. Just give me a moment here. And so since the charges are the same, it really doesn't matter if I say it's positive or negative. I'm just going to assume it's negative. And I'm going to draw a free body diagram here on the charge. Okay, so I'm drawing a free body diagram just to see what interactions of forces we have here. And so we know that both of the spheres have a mass. So that means that there's going to be a weight. There's going to be a force going down that has to do with the mass and gravity. So I'm going to write that down here. This is going to be the weight, and the weight is equal to the mass times gravity. Okay. And this is going to be equal to, in this case, it's 2 grams. Okay. So 2 divided by 1,000, I always get the multipliers wrong. That's 0.002 if I'm not mistaken. I want to get that.
It's there.
Oh, it's already in kilograms. Thank you. Good. 0.002 kilograms. And it's 0.002 kilograms multiplied by 9.2 meters seconds squared. I'm going to assign some people to give me values here. So Andrea, could you please calculate that value while I write down some other things and give it to me?
Sure.
Okay, thank you, Andrea. And we've got some other forces happening here. There's going to be a force going this way. That's going to be the electrical force.
Professor, I already got it.
Oh, perfect. Thank you. What value is it, Andrea?
It's 0.01996.
0.01996, and these are newtons. Thank you. Thank you, Andrea. And this force here that I'm going to call FQ is going to be the electrical force that's happening between the charges. Okay. And we know that FQ is going to be given by Coulomb's law. It's going to be K, in this case, Q1 times Q2 divided by the square of the distance, But we know that both charges are the same, and so this is FKQ squared divided by R squared, okay? If at any point anybody has any questions, let me know. And lastly, we've got a force that is going this way. That's going to be the force on the string. I'm going to call it Fs. Okay. That force is going to be the force of the string that's holding it to the ceiling. Okay. And there's going to be an angle to that force. That angle is going to be right here. What is the value of this angle here? Anybody? What is the value of this angle that we have here of the force?
30? 60?
Let's see. And let's
75.
let's try to make this a little bit more systematic and mathematic and just check it there. We've got a triangle that's formed here. Okay. We have a triangle that's being formed. That triangle is this triangle here. That's the one I'm representing. And so for this triangle here, we know that this side is 0.3 meters. And if this angle is 30 degrees, then what would this angle here be?
15.
It's this exactly. Thank you, Estrella. It's half. It would be 15 degrees. Okay. And this angle here is 90 degrees. And so therefore, this angle over here would be how much?
75.
75, correct. Thank you. 75 degrees, which is the difference between 90 and so this angle here is going to be 75 degrees. It's the same proportion. This is 75 degrees, and actually this angle here is 50. Okay. Over here on this side, over here on this side, we actually have the calculations to find this distance here. Okay. This distance, we're calling it B. And this distance over, let's call this one A. And this one over here, this is equal to C. And there's a question in the chat. I'll go to that question in a moment. Okay.
Professor, I don't understand from where are you starting the free diagram? Like, where's the middle point, like the center?
Okay, good. The free body diagram. So for the free body diagram, Andrea, I am taking any of the two spheres. We can do it for any of the two spheres, but I'm doing the free body diagram here. Okay. In this.
Okay.
And so if I'm doing the free body diagram here, because I can also do it on the other sphere, and the result would be the same, just that the forces would be going the other way. I can do it in either one. And so in this case, for this free body diagram, this is where I have this force here, which is the string. I've got the weight going down, and I've got the electrical repulsion force, because they're the same going this way. Okay. Is that clear, Andrea?
Yes, and the blue one, what's the name? F what?
Oh, I wrote that down a bit smudgy there. I'm calling it, since it's a string, I'm calling it FS.
Okay, thank you.
A bit smudged there. Thank you.
Professor,
Yes, go ahead.
I also have a question. For example, we are always going to be doing this if we want to calculate the magnitude of the charge
Well,
in this example. But
yeah, there's many ways to approach this problem, but the way I'm doing it here is that, and that's what I recommend, is that when we've got situations where we have many things interacting, we first try to represent all of the forces. And once we represent all of the forces, then we use these expressions to find whatever we're looking for. Because right now what we're looking for, Estrella, is a charge, right? But this exact same problem, we would use exactly the same procedure if we knew the charge but wanted to find the distance, for example.
Okay, so where
So-
you're first finding the distance.
Yeah.
Yeah, right.
Yeah, so in this case, depending on how you approach it, first you represent the model, which is the free body diagram, represent the forces, and then out of that, you find whatever is missing. That in this case,
Okay.
it's gonna be the charge. It's the only value that we don't have. Okay.
Okay,
Is that
thank you.
clear, Estrella?
Yeah. Oh, another question. Why do we need to use the weight?
Oh, because the system is in equilibrium. So what the system being in equilibrium means, Estrella, is that those charges are suspending and are not moving. Okay.
Okay, yeah.
So if the charges don't have weight, there's nothing hold the string. You notice that the string forms an angle here, right?
Mhm.
So that angle means that the string has an X component and a Y component. Both of those need to be compensated so the ball is floating. So if I don't consider the weight, then there's nothing pulling the ball down to compensate the vertical force. So all of the forces in the end have to be zero, okay? So if the problem is giving us the mass, it means that the mass has to be considered. And if the mass is considered, it means the weight has to be considered, okay? Is that clear?
Okay.
Does that make sense?
Yes, thank you.
Now, Estrella's question is important because there's going to be some situations where the situation is going to tell us these particles are so small that we don't care about the mass. The particles are so small that the mass is irrelevant. There's going to be some situations like that. This is not the case, okay? And so here, using trigonometry, we can find the distance B of this triangle, and finding that distance B, which is half of the distance, the double of that is going to be the complete distance or between the two spheres, which is this distance R. And that's going to be something we need to use because the electrical force needs that, okay? Okay, so there has to be some sort of equilibrium that's achieved here. So we're going to have a sum of forces in Y that's going to be equal to Fs times the sine of 75. Why is that one positive? Because Fs is going up, okay? And so since it's going up, the vertical component is going to be on the positive axis, minus the weight, which we already know. From here, we know we can find the value of Fs, which is going to be the weight divided by the sine of 75 degrees, okay? Viviana, could you help us out with that calculation, please? And then when you have that, give us the value of Fs.
Professor, we can also use the sign of a.
Can you say that again, Andrea?
I think she meant that.
Like use.
The sign of 110 or 105.
Yes, it says my connection is unstable. I'm going to wait for that to go up. I think mathematically it's going to give you the same value, but I'm not sure if you use 105 if you're going to get a different sign. So you just have to be careful about the signs. Okay, so that's why in the free body diagram, when we're going to be using the components, we usually take the angle that goes from the x-axis to the force. Okay. But I think mathematically you would get the same value, but I think you would get a negative sign. That could be misleading.
No,
Okay.
yeah, I have the same.
It's the same. Sometimes, depending on the some sines and cosines are going to give you the same signs or different. So if you use 105, you should get mathematically the same value.
You
And
said
then-
we have to use the one that is closer to the x-axis.
That's just kind of like a guideline, but if you use 105, I think you would get the same thing. So instead of using 75, use the complementary angle, which is this one here, and you should get the same, value. Does that make sense, Andrea?
Yes, thank you.
Okay. And then we have the sum of forces in X is going to be equal to FQ minus FS multiplied by the cosine of 75 degrees. And from here, we can find the value of FQ, which would be FS divided by the cosine of 75 degrees. And so just to verify the calculations, Viviana, do you have the value of FS?
Yes, I got 0.0206.
206 newtons. And if we have that value, we can find the value of FQ. Iskra, could you help us with that calculation, please? So FQ, Viviana already gave us the value of FS, and so FQ is going to be FS divided by cosine of 75. And remembering that FQ is KQ squared R squared, from this expression, we have that the charge, which is what we're looking for, is going to be equal to FQ multiplied by R squared divided by K squared. So, Iskra, when you have this value, let me know.
I think it is 0.0223.
0.0223 newtons. Okay. And with this value of FQ that we have, I'm going to bring this over here. Q then.
I got another thing, but I don't know. Yeah, me too.
You got a different value?
Yes.
Okay. Check.
Because if I don't have the vocabulary on.
Okay, and check maybe if it's not in, maybe in radians. Remember, it's very important when we're doing the calculation, maybe some calculators, and even if you're using it on the sub, by default have it in radians. So we got a different value over here. Let's corroborate. Enya, what value did you get?
It's 0.079.
0.079. Viviana, does that check out?
Yes.
0.079. Newtons. And so Q, which is what we're looking for, again, is going to be the square root of FQ, which we just found. Multiplied by the square of the radius, and R is this value that we have here, divided by the constant K. And so if we substitute all of those values, what value of Q do we get? Which is should be the solution to the problem. Let's see. Let's see somebody over at home. Jose Miguel, could you help us with that calculation, please? We've already got all the values we need.
Did you call me?
Yes, Jose Miguel, could you
Oh,
help
sorry,
me?
my internet was not working.
Yeah.
What part?
Don't worry, can you help us with this calculation here? The last one, this one here on the bottom, the one that's in purple?
Yes.
And that should be the solution to the problem. And remember, you guys at home, I know that in general, we might be having internet issues, and the internet issues can happen. Either internet here could be faulty, or internet in your houses can be faulty, or we could be dealing with those problems. So that's why remember that I'm recording the sessions. All the sessions are recorded and are going to be uploaded to the playlist. So you can review if anything wasn't clear, or you need to review it at some other point, you have that. Okay. Okay. Jose Miguel, how are we doing with the calculation?
I wanted to ask, is it where it's like 0.07, is it a 9?
0.079. Yep.
Okay.
That was one of my ugly nines.
Professor,
Yes, go ahead, Estrella, please.
do you think that you can explain how did you get the sum of fx?
Sure. Let me go through that again. Let me just write this one down a little bit clearer. It was 0.079? Was
Yes.
it 0, right? 0.79 units. Okay, Estrella. So the sum of forces in X, the sum of forces in Y is clear, Estrella?
Can
Or
you explain it too?
Yeah,
So yes, to get it very clear.
Yeah, let's just go through it again. Remember that when we have the free body diagram, there are going to be vertical components, and there are going to be horizontal components. The vertical components are the Y's, and the horizontal components are the X. Okay. So what we do is that when we do the sum of forces or of components, we're going to add the X components and the Y components. Okay. So for the sum of forces in Y, we're just going to look at the vertical axis. Okay. So when I have something in diagonal like Fs, that means that one is going to have a vertical and a horizontal component. The vertical component is going to be the force multiplied by the sine of the angle made with regards to X. That's why it's Fs times the sine of 75. Why is that one at the beginning and positive? Because Fs, the vertical component is up. Okay, and up is positive. Okay, the weight is going down, so that's why it's minus the weight. Why doesn't the weight have an angle? Because the weight is completely aligned to the axis. Okay, is that clear?
Yes, it is.
Okay, now, and by the way, I wasn't explicit about this, but these are equal to 0 because we are in equilibrium. Okay, now with the forces in X, it's very similar. First, we look at the X and we look where is the positive of the X? The positive is going right. And so what do we have going right? FQ. It doesn't have an angle because it's completely aligned with the X, and that's this one. Fs is going to have an X component, but it's going to the right, to the left, I'm sorry. And if it's going to the left, it means it's negative. And so it's going to be Fs, and when we calculate the X component, it's going to be the cosine of the angle. That's why it's minus Fs, cosine of 75. And this is equal to 0 as well, because we are in equilibrium. Okay. Is that a little bit more clear?
Yes, it is.
That's right.
Thank you, Professor.
Professor, I have a question.
Go ahead.
Why didn't in forces of Fx, we didn't pass FQ equals Fs cosine 75?
In this one?
Yes.
Okay, could you ask that again?
Why didn't we put FQ equals Fs cosine 75?
Oh, I just jumped a step. I didn't do that step. I'm going directly. So here, since this is equal to 0, this is actually equal to FQ. Oh, I'm sorry, Vivian. I understand what you're saying, and I made a mistake here. Thank you. This is being recorded, so send this to my wife and make mistakes. Thank you, Viviana. I made a mistake here.
I was like breaking my head. I was like, why?
Oh, no. You're right. I'm sorry. I made a mistake here. And thank you for that. FQ, I'm sorry, is going to be equal to Fs cosine of 75. I'm sorry. And so this calculation, we need to do this one again. Can you do that, please, Viviana? Could you help us out here?
Yes.
And we're gonna have to use a different value there, Jose Miguel, for what you were calculating.
Yes,
Yeah, thank you for catching that, Vivian.
I got 5.33 times 10 to the minus 3. Yes, I got the same.
So the -3. So now please, Jose Miguel, use that value for the calculation of Q, please. Thank you, Viviana. Sorry about that. The moment your brain starts, lift your hand and stop me there, because again, people make mistakes and professors make mistakes as well. And it's better to catch the mistake here and not when we're done. So thank you. So how are we doing with the calculations?
yeah, I already have it.
Okay.
I think it's 1.154 times 10 to the minus 7.
1.154
Times 10 to the minus 7. Yes,
coulombs.
cool.
Yeah, let's just verify that value, the rest of you. Just see if we got that correctly, and remembering we've got a square root there, and we've got a square root, and
I
we've
got
got
the same.
the same, and
It's to the minus 7, right?
yes. Do a better 7 here, but yeah. Okay, so this will be it. Okay. Let me take a screenshot of this. Okay, questions with this one? There's another, I'm gonna let you guys review that, but there's another path of actually doing this, just without taking into account the forces and just kind of taking into account trigonometry, which is also valid, but I do want us to practice the free body diagrams. That's why I'm also giving you this alternative. Okay. Okay, so questions with this one before we go on to the next ones.
No question.
Over here, over at home. Before I wipe the screen.
No, I'm only copying.
Okay, perfect. Remember, again, and I'm gonna be reminding this to you guys, all of this is being recorded, and all of the solutions with the procedures are in the updated PowerPoint presentation, okay? Or in the updated PowerPoint presentations that I update after every class. So if for any reason you haven't written down the procedures, you can you can review them later on. Okay. You're pointing at the screen, Viviana. If I made another mistake, please let me know now.
No.
Or forever, or because again, I do make mistakes. Okay. I'm gonna send the screenshot in the chat just so you have it there. Okay, I'm gonna clear and jump over to the next one, okay? Okay. Oh, this was a really beautiful way of solving a problem. And so for this problem, for problem number 10, we have a situation where we've got 3 charges that form an equilateral triangle. Okay. We've got 3 charges that form an equilateral triangle. Q1, Q2, and Q3. We know it's an equilateral triangle, and we know the distances or the sides, and all the charges are the same for the problem, if I'm not mistaken.
Yes.
4 times 10 to the minus 6, or 4 microcoulombs. And the problem is asking us to find the net force or the resultant force in each of the vertices for this situation, for each of the vertices. And so, I believe this was done by the Angels, and this was, you worked on that one, right? And you, okay, the very nice procedure. And so you've got the procedure there. There's a bunch of calculations, but I just wanted to go through and make clear how we approach the problem. So just in general here, and you know, walk us through each of the situations and what you did.
Okay.
And try to speak loudly so people that are far at home can hear you.
Okay, I'll try to talk loud.
Okay. I think that level of volume is okay, or else they're gonna think you're shouting angrily at them, and that's something that could hurt
So,
feelings.
The problem stated that we had three, how do you call them?
3 point charges.
The charges, yeah.
Oh, by the way, it's important, the terminology we use point charges. And because we're gonna be talking about things with geometry. Why do we say point charges? Because it's literally a point in space that doesn't have a dimension. So if it's a point charge, it's just a point. It's different if I told you it's a sphere, or it's a cube, or it's a disk, something that has a dimension. We don't care about the dimensions, that's why we call them point charges. There's 3 point charges in space.
Okay. So we had the 3 point charges and they were placed like in an equilateral triangle. So the sides should be equal. And that's what I wrote on the data part. Then we had the radius of 20 centimeters or 0.2 meters. The angles that were 60 degrees because those are the angles of the equilateral triangle. And the charges. Then I made a specific free body diagram for each of the point charges because they're placed on different situations. Then I calculated the forces with the formulas that we have because we had the constant and the charges. And since it was the same charge for all of them, it could have been done with the Q squared, but I multiplied them either way, the both of them.
Let's take a quick pause there for a couple of things. Now, let me pause there and go a little bit back because there's a very important part here of the problem that we need to understand. You've done three free body diagrams for each of the situations. Let's just understand here what those situations are. Because it's important for the development of the problem. Then we can go on to the calculation. So we've got the 3 charges. So this free body diagram, number 1, we are located here. Okay, we're located here for 1.
And what is it?
Because of the forces.
Oh, okay. Why are the forces going that way? First off, the 3 charges are the same of value and of sign. Okay,
They're negative.
they're negative. They're specifically negative. So if we are Q1, when we put the free body diagram someplace, it means that's where we are. So if you're Q1, what is the force with regards to Q2? Where is that force going to be pushing you towards? Vivian.
Opposite.
Yeah, and so if we're here, that force with regards to Q2 is going to be pushing you this way. And if you're there, what is the force with regards to Q3? Where is that force going to be trying to push you towards? Because it's a repulsion force. It's going to be trying to push you this way. Okay, is that clear?
Yes.
Okay, was that the question?
Yes.
Yeah, and so and it's important here with the charges. We're basically placing ourselves with the charges, and we're trying to interpret the rest of the charges or electrical fields. What are they doing to us? And each of those, where it's trying to push us. Now, there's 2 forces trying to push us, one to the right and one downwards to the right. In the end, there's going to be a resultant force that's going to make me move somewhere. Okay, that's what we're trying to find. Okay, so that's situation 1. Okay. Situation 2, now, which is this one, now we are placed here in Q2. And so now if I'm in Q2, what's happening? Both of the charges that are in the bottom are trying to push me. In this case, Q1 is trying to push me this way, and Q3 is trying to push me this way. That's why the forces are going up, okay? And lastly, the third situation, which is this one, now we are located here in Q3. And so what's happening in Q3, it's actually going to be the opposing situation of Q1. Q1 is going to be trying to push me this way, and Q2 is going to be trying to push me this way. Okay, and that's how the three free body diagrams are constructed. Okay. 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 Now go on in. I just wanted to point out where those came from.
Okay. So then we calculated the forces, and I did it 3 times just to make sure, but it would have been just fine just doing one because we had the same charge for each one. And
So the magnitude of the forces is actually going to be the same because since the charges are the same and the distances are the same, the force that Q3 acts upon Q1 is going to be one value. It's going to be exactly the same magnitude of the force between Q2 and Q1 because they're the same value and the same distance. You verified that anyway doing the 3 calculations, and that's fine. It's 3.6 newtons. So regardless of where it's pointing, the magnitude is going to be 3.6 newtons. If the charges were different and or the triangle was not equilateral, the forces would not necessarily be the same. But in this situation, it is. Okay, go ahead.
And then based on the calculation of the forces and the free body diagrams, we made the sum of the forces on X and on Y. And we just substituted with the answers or the results that we have obtained earlier, and we got them, and then we calculated the net force for those.
For each situation.
Yeah.
Now, in this case, each of these is going to have a sum of forces in X and Y. And we follow the same conventions we've done for the other ones. So for example, for situation 1, the sum of forces in X is going to be equal to FQ3 plus FQ1 times the cosine of 60 degrees. The sum of forces in Y, the only force that's acting in Y is going to be negative FQ1 times the sine of 60 degrees. This would be situation 1. And each of those is going to give us a value. The net force is always going to be the Pythagorean relationship of the sum of forces in X squared times plus the sum of forces in Y squared. And the direction or the angle that force is going to have is going to be the inverse tangent of the sum of forces in Y divided by the sum of forces in X. And so this same analysis was done. What I wrote here is what Enya has over here. Okay. And the same analysis is replicated for each of the other situations. Okay, for Q2 and for Q3. And we get the net values and the resulting forces. Okay. And so this was a clear procedure and way of doing the calculations. Okay. Okay. Estrella, could you please go ahead, please?
Yes, for example, they calculated the charge 1, and what they need to substitute in the formula is the force net, or
Could you say that again, Estrella?
they need to calculate the charges or
No, we're already given the charges. What we need to
Mhm.
know is the resultant force that's being that's being exerted on each of the charges. So we know the values of the charges, but we want to know the complete and total force that the other two charges are exerting on the third one. So for example, if we're located in charge 1, we want to know the resultant force on that charge with regards to charges 2 and 3. And we're doing that for each of the vertices of the triangle. So what we're looking for is the total force
okay, of each one.
of each one. And that's why we analyze each of the 3 situations separate.
Okay,
Okay.
okay, thank you.
Okay. Okay, additional questions with this one. Okay. Let's I'm just looking at something here that I'm trying to verify. I think we have to double check here, Enya, in the calculations, and we're going to be making that correction. Maybe I'm going to make that correction in the slide. I think we have to double check the calculations of the angles. Okay. Because in case number 2, the forces in X should cancel each other out. Okay. So we need to the procedure is correct. The procedure is correct, but we need to double check some of the calculations. Okay. And actually this problem, I'm going to update the slide with the calculations. Because, for example, in this situation, you've got FQ1 and FQ2, and these are the same value, 3.6 and 3.6. Both of them have the cosine of 60 degrees, and both of them are going in opposing directions. So the X forces have to cancel each other out. This has to be, the sum of forces in X has to be 0. And if this is 0, the angle is going to give you 90 degrees. So the resultant force should go directly up. Okay, so the procedure is correct, but we need to double check the calculations. Okay, and I'm going to update this slide with the calculations because I think that we did make some mistakes there, even though the procedure is correct. Okay. By the way, remember that I mentioned that we've got the playlists of the videos of the class. There's the complete videos of last year's course, and actually this problem, there's also a solution procedure from last year because the students had a lot of problems with this problem in particular. And so in the video that should be around February 1st or 2nd week of February of 2021, you can find also another version of the complete solution of this problem. Okay, that you can cross-reference. But the procedure is correct, but we need to double check the calculations. That's the only thing. Okay. Okay. I'm going to jump over to the next problem. Okay. Problem number 11. It's similar to problem 10, but instead of having the charges in triangle, the charges are in a straight line. Okay. And we've got charges, we've got 3 charges. Now the charges are of different values. We've got Q1, Q2, and Q3. Each of them are located in a certain position. They have a certain distance as well. The distance isn't given there, but the distance is one of them is 0.5 meters and the other is 1 meter. And they're asking us to calculate the resultant force in each of the charges. So similar to the other one, if we do an analysis for each of the charges. So let's say that this charge here is Q1. There. this is Q1, this is Q2, and this is Q3. This is the analysis in Q1. There's going to be two forces. One force is going to be a repulsion force, and the other force is going to be an attraction force. And we calculate each of these two using Coulomb's law. The force between Q1 and Q2 is going to be the electrical constant K multiplied by the two charges and the distance that separate these, which is 0.5 meters. This isn't given here. The force between well, actually, the separation is the same. The force between Q1 and Q3 is going to be the electrical constant multiplied by charge 1 and charge 3, and the distance is going to be double. And this gives us these two forces. Once we do the calculations, we get the difference between the one force is going to the left, the other one to the right. In the end, we get 0.54 newtons. The resultant force is going to be 0.54 newtons going to the this is 0.864. And so this is negative, and it's going to be going to the left. If we do the same analysis, but now we're going to be located in Q2, we're going to have the force between Q1 and Q2 is Q2 multiplied I'm sorry, Q2 and Q3 is Q2 multiplied by Q3, and the distance is still going to be the 0.5 meters. We get this one. We already had the force between Q1 and Q2. The force is going to be the same. And in this case, the force is going to be positive, and it's going to be going to the right. Lastly, if we locate or place ourselves in Q3, we're going to have we already calculated the force between Q1 and Q3, and we already calculated the force between Q2 and Q3. The magnitudes are the same. Now we only subtract them. This is also going to be negative, and it's going to be going to the left. Both forces are going to the left, so the resultant force is also going to be going to the left. Okay. So this is a similar problem to the one we had with the triangle, but all the forces are in the same line. Okay. And in the end, we're calculating the net force. And another way of interpreting the net force is in what direction would that charge be moving because of the effect of the forces of the rest of the charges. Okay. Okay. Questions with this one, and questions with the problems up to this point. Okay. Next week, you guys are going to have a homework tasks. A homework test that is going to be another set of problems, so we can keep practicing this. Okay, we're good on time. Okay, questions before we jump over to the next thing? Nope. Okay. Okay, so before we wrap up today, we're going to be talking now about something that's called an electrical field. So we already said that if we have an electrical charge or electrical charged bodies, and these are going to be in space and they interact with each other, there's going to be a force. And that force is going to be because of the interactions that these charged objects have. It's very similar to gravity. So right now, all of us are stuck to the ground because of gravity, right? But is it clear that we can't see gravity? It's something that exists and we're being pulled down. Every body or every planet has gravity, but we can't see it. There's actually something that's called a gravitational field. Every celestial body is emanating a field, and that field is what's pushing us downwards. That's called a gravitational field. Yeah. And it's pushing us downwards depending on our mass and other stuff. But imagine that we have the Earth, okay? The Earth is let me try to draw the Earth. This is the Earth, according to me. There is a gravitational field that we don't see. that has certain characteristics that if I place something within that gravitational field that, well, let's not put a circle there. Let's put a person there. If I place something that has a mass within that gravitational field, the mass, when it interacts with that field, generates a force that pulls it towards the object. That's basically the way gravity works. But is it clear that we don't see those lines that I just drew there? We don't see them. Is it clear that the moon has those lines? Saturn has those lines. Any object with mass has those. And they had those because in this case, the Earth also has a mass, but it's a much larger mass than this one that this person has here. Okay, we okay up to that point? Well, with charged objects, it works the same way. And we actually already saw that. And I'm gonna remind us of this. Yes, go ahead. We already saw this. Remember that we talked about the we did this exercise in the simulator. Remember that you can click that and go to the page. If I grab a positive charge and put it in space, I get those arrows. That's the electrical field. And the difference between charged objects and objects with mass is that the mass gravitational field is always going to be pulling inwards. In the case of charged objects, depending on if the object is positive or negative, is if the electrical field is going to be going outwards or inwards. And so for a positive charge, those arrows represent the electrical field. And the electrical field is going outwards. There's two characteristics that tell us how strong an electrical field is. That's going to be a question in the exam. What are those two things that are going to tell us how strong the electrical field of that charge is? When I drew the Earth, remember that I drew the Earth had a mass that was an M, a large M, and then the person was a little m. So the larger the mass, the larger the gravitational field. The smaller the mass, we don't have a gravitational field because our mass is so small. With regards to a charge, what is going to be the main factor as to how strong its electrical field is?
The amount of charge.
The amount of charge. So if I have a 1 nanocoulomb charge, it's going to have a certain field. If I have 100 nanocoulomb charge, the field is going to be stronger. So the field is going to directly depend on the charge. And the strength of the field is going to depend on how far or close I am to the charge. Andrea, go ahead, please.
What did Enya say? The amount of what? It's because I
Charge.
can't hear.
The amount of charge. So the strength of the electrical field is going to depend on the amount of charge. The larger the charge, the larger the electrical field. And the strength of the electrical field is going to depend as well on how close or far I am from the charge. So fields are going to radiate. Okay, so the further I am, the less the field is going to be perceived. The closer I am, the stronger the field is going to be perceived. And we know that if I grab a negative charge, the negative charge is also going to have an electrical field, but the field is going to be going inwards. Okay. And I know that if I grab two charges and put them together, the fields are going to interact. And that interaction of fields is what generates the electrical forces. Okay. Either attraction, like that one, or repulsion when they're the same. Okay. Okay. Now, electrical fields, right now we're just talking about an electrical field of a point charge, something that doesn't have a geometry, doesn't have a form, something ideal. It's just a point in space that's emanating energy. But we could have different situations we could have a cylinder, and the cylinder has a charge. So how is an electrical field, how is the electrical field of a cylinder gonna behave? How is the electrical field of a sphere going to behave? Or how is the electrical field of a plate or something that's that has a certain length and width? How are those going to behave? And those are also going to be important for us. Can somebody think about why would it be important for me to understand how an electrical field of a cylinder behaves? Does anybody have any ideas about that? Look at the image there. This is a sort of a conceptual representation, but here is a cylinder. And the cylinder has a certain electrical charge. The cylinder is different than a point because the cylinder has a geometry. Why would it be of interest to know the electrical field of a cylinder? Ideas?
You can use it in like for lifting maquiladoras when you're working with metal parts or metal scraps.
Well, let's go with that, Javier. Javier, for those of you at home, Javier was a bit far away, but he said he mentioned, paraphrase, something like we could use it in maquiladoras because we have things that are metal and stuff like that. Well, yeah, it's important to know about electrical fields and magnetic fields of things because they interact. So, yeah, if I have a machine and that machine is electrical, it's connected to electrical power, and that machine has parts, it has metal parts, it has different parts, and it has moving parts, then there's a possibility that that machine is going to be generating electrical energy or getting charged, and there's going to be an electrical field around it, or maybe even a magnetic field, right? And what happens if suddenly I'm moving a product that's metal and I'm walking close to that machine that's generating this electrical field? What's going to happen with whatever other product I'm holding? There's going to be some sort of conduction because we already mentioned that electrical energy can be transmitted by contact, but also by induction. And so let's imagine that I'm walking close to a machine that's generating an electrical field and I have an electrical circuit and I'm walking next to it and suddenly those fields interact, I'm going to negatively affect the circuit. That's why machines have certain precautions that have to do with how we, I don't know if you've heard this concept of how we ground machines. There's an electrical concept that's called ground. And ground is literally connecting something to something larger than itself that can absorb that excess electrical field. So instead of the machine is generating an electrical field, but I'm going to connect that machine to something so much larger than that machine. Remember the example of the two glasses of water when I connect them, that they try to balance themselves out? The two glasses of water were of equal size. But now imagine that I've got a larger one and a smaller one, and everything tends to be to equilibrium. So there's this machine that's generating a lot of electrical and magnetic energy. I'm going to connect that to something that's so much larger than itself that the charge is going to go to the larger object, not the machine. Does that make sense?
Like in cars, when you run out of battery, then you connect them.
You make a connection to transmit the energy, correct? Yeah, and by the way, for any of you who have done, your batteries have gone dead and you connect to charge with another car, there's a procedure to do that. The thing that some people do that's extremely wrong is I'm going to connect red to red, black to black. You shouldn't do that. That could damage either of the cars. There's a reason one of the clips goes to the chassis. How do you say that in English? Chassis. It's just chassis.
The chassis.
The chassis, correct, thank you. The chassis of the car. That's why you connect it there and not to the positive. Because again, there's this concept of charge going to some place that takes it there and leaves it where it doesn't affect us in a negative way. Now, I'm saying it generically to see if you guys get the idea. Again, I have this machine or whatever is generating a lot of electrical charge, and I want to connect it to something that's much larger than itself, where the charge can go. Are we okay up to that point? What is something that's extremely larger than all of us here on Earth?
The sun.
Well, the sun isn't on Earth.
Oh.
You're right, but the sun isn't on Earth. Here on Earth, what is extremely larger than any of us?
The sea?
Well,
The ocean?
you're getting close. You said Mount Everest, the ocean. Where are the sea and the ocean located?
Here.
The Earth. The Earth in itself is a huge thing that's much larger than anything that's on top of it. Okay? That is why electrically, you notice that in your electrical sockets, in most of them, there's 3 connections. One is the line, the other is called the neutral. The one in the middle is called ground. And it's literally called ground because it's connected to the ground. And actually in Spanish, you know how they call that electrically in Spanish? Tierra. And why is it called tierra? Because it's connected to the earth. It's literally grounding something, electrically grounding something is having literally a connection to the earth. So electrical charge or magnetic energy can go there instead of staying in the object. Excess electrical or magnetic energy. Okay, are we okay up to that point? Have you noticed sometimes when any sort of electrical layout or connection is faulty, that sometimes you get shocks from things?
Yeah.
So you might have a house or you might have a room where the electrical connections are faulty, or maybe there's a lot of connections done somewhere, and suddenly you're walking around and things start giving you shocks. Or suddenly you turn on the microwave and the lights start flashing or whatever. That's because it's not properly grounded. And grounding something, which is that 3rd cable, helps that excess electricity or electrical charge go there. But going back to the example, why would a charged cylinder be important? Well, are you guys familiar with cables? So this,
Yes.
are these square? Is this, if I cut this in the middle, is this a hexagon? Is this a square? Is this a triangle? It's a cylinder. Is that clear to everybody?
Yes.
Why don't we make cables like triangles? Why isn't this cable a triangle? Because it's impractical. It's impractical. To conduct something, it's easier to have a wire. And if we look at a wire is a cylinder. This is a cylinder. If I grab this and cut it, it's a cylinder that can be bended, but it's a cylinder. Whoops, disconnecting. Over at home, are we clear on that? Look at any cable around you. All the cables are bendable cylinders, right? Are we okay up to this point?
Yeah.
So electricity is going through this cylinder. So depending on the electricity because even if this is just a USB connection, there's electricity going through it. Why is this covered in plastic? Buenas tardes. Disculpa. Adelante, sí. No importa que sigamos en la clase, ¿verdad? Okay. It's bendable, okay? Do you notice that all of the electrical cables are usually surrounded by plastic, right? You usually don't see an electrical cable that's just the metal there. And if you see one, you're going to touch it, right? No, you're not going to touch it. Why is it covered in plastic? Because plastic is an insulator. And the plastic, and by the way, if you cut any of these cables, you're going to notice that there's even more layers of insulation inside. That is because a plain metal cable or like those metal parts that you were thinking about, Javier, in the company. Any sort of conductor, when I put electrical energy into it, is going to generate an electrical field. I can't, it's any object that has an electrical charge is going to generate an electrical field. There's no way to go around that. And by the way, if the charge is moving, it's also by default going to generate a magnetic field. I can't go around that effect. So how do I compensate that? I have to isolate them. And that's why there's a bunch of things covering. So that's why it's important or interesting to know how an electrical field of a cylinder behaves, because a cylinder is basically a cable. Okay. The other situation that we're interested in is going to be parallel plates. Yes. Oh, it fell down. Don't worry, I'm not going to be using it. Well, if you can reach it, I'd appreciate that. Thank you very much. Thank you. The other situation that we're going to be talking about is charged plates. You notice here in this drawing here, we've got two plates here. Let me see the cursor. We've got two plates here. And these plates have a charge. So instead of the charge being in a point or a cylinder, the charge is going to be in something like this. It's going to be in a conducting plate, like a metal plate. There's a very interesting phenomenon that happens when I have two charged plates and I put them together. That kind of looks like a sandwich, right? There's two plates and there's something in the middle that right now looks like nothing. But and I always try to transmit this example. This is actually going to be unit 2. That's an electrical sandwich. An electrical sandwich means I'm grabbing two things that are conducting, like metal, and I'm putting something in the middle. Would you all agree that a sandwich can be good, bad, tasty, healthy, or not, depending on the bread and what I put in the middle, right? And right now is that time where you're going to start getting hungry. So think about a sandwich. Well, the same thing happens electrically. Depending on the type of metal or conductor, depending on the type of metal, and depending on what I put in the middle, I'm going to generate an electrical sandwich. And that electrical sandwich has a name. The name is a capacitor. And an electrical sandwich, or that thing that's called a capacitor, it's basically something where I can store energy. I can store energy. Have any of you noticed, I hope you haven't, but if you have, I hope you've been careful. Whenever you have an electrical device, there are warnings on the device that say, do not service or do not open the electrical device and start working on it, even if the electrical device is disconnected. Have you seen those warnings? Grab your PlayStation, grab whatever device it says, do not service, even if it's disconnected. Because you say, if the electrical device is disconnected, that means that there's no energy there. So if I start opening and touching it, there's nothing can happen because it's disconnected, right? No, because there are things called capacitors. There's these little things in electrical boards that actually look like these little tanks. When you look at them, those store energy. So if we have 110 volts, we might have one of those little things, which internally is actually just a sandwich. It's two metal conductors and something in the middle. That's going to store energy. So even if the device is disconnected, capacitors are going to store energy. They're going to store it for a certain time. They get discharged after a certain time. But you might have the device disconnected and you say, I'm going to open it up and start fiddling around in it. There might be a capacitor there that has the equivalent of the device being connected of energy stored there. So you could get an electrical shock and you could actually be hurt or damaged by that. We're going to be talking about these examples moving on. Okay. And actually the charged plates situation The capacitor situation, we're gonna talk about that in unit 2. All the unit 2 has to do with capacitors. And so before we close up, yes, just about. How do we define mathematically, how do we define an electrical field? Now, mathematically, to be doing calculations, an electrical field mathematically or formally is defined first off with the letter E. The letter E is going to be the letter we use to represent an electrical field. And there's a couple of ways to represent an electrical field. The first way is that the electrical field is going to be the force exerted around the object by unit charge. Okay, so it's F divided by Q. And depending on the geometry of the object, then there's going to be different representations of electrical field. So each of these situations that are shown there, the point charge, the cylinder, the sphere, the parallel plates, each of them are going to have a different representation of their electrical field formula. And we're going to find those formulas and we're going to demonstrate. The first situation that we're going to look at is the electrical field of a point charge. So a point charge, which is the ones we've been talking about up to this point, are going to have electrical fields. So it's a point charge, depending on if it's positive or negative, the field is going to be outwards or inwards. And so if the electrical field is the force divided by Q, then the electrical field with regards to the charge is going to be K multiplied by the charge divided by the square of the distance. So if I have a charge in space that has a certain value, the electrical field is going to be the constant K. We're going to be using that constant throughout, multiplied by the value of the charge, and the strength of the field is going to depend on how far or how close we are. And that's the first representation or expression of electrical field, okay? Which is KQ divided by R squared. And it's going to be radiating, so it's going to be going outwards, either pointing outwards or inwards, depending on if it's positive or negative. And if I have many point charges in space, the electrical fields are going to be related, and similar to a force, it's going to be a resulting electrical field or combination of those. Okay. Before we go, let me leave you with something you can do. This is actually going to be an activity for you guys next week. It's going to be a mandatory activity, but everybody's going to get extra points depending on how you do it. So it's going to be something that all of the houses need to do, but depending on how well you do it, you're going to be getting some extra points. And so it's electrical field hockey. And so this is going to be the challenge I'm going to ask you guys to do. And next week, I think Friday of next week, we're going to see who does the best on this. And I'm just going to show you this, and then we're going to go. This is electrical field hockey. We've got a positive charge, and this is the goal. It's like, or football, whatever you like. If it's football or hockey or whatever. And basically, I want the charge to go into the goal. How am I going to do that? Well, I need to push it or move it. How am I going to move it? I'm going to put electrical charges that generate electrical fields to either push it or make it move wherever I want. So this is the most simple example. I've got a positive charge here. I am going to create. Oh, here are the charges. I'm going to grab another positive charge, and I'm going to put it here. Notice that depending on how close or far I am, that arrow represents the strength of the force. I'm going to put it here. And then I'm going to click start. So the electrical field is making the charge, the other charge go forward, and there's a goal, right? We can actually look at the electrical fields. Here. I'm gonna reset. This is the electrical field of the charge I'm putting. And this is the charge I'm moving. So if I start again, it's gonna go there. Okay. And I got a goal. That's easy, right? That's not the bonus. The one I want you guys to do this one. So I don't know. I'm just gonna do it randomly. I'm gonna put one charge here. Nope.
Oh,
I needed to go over there. I needed to go to the goal.
you don't have lives.
No, you don't have legs. No, no, no.
And you cannot touch
I
the.
thought it was gonna bounce off.
Me
but it
too,
just
Yeah.
me too.
I was like, oh. This is
Oh, no,
easy.
because we're, that's a good observation. Maybe I'm putting this, it's not gonna bounce off because we're considering right now that these things don't have any mass.
Okay.
So they're not, there isn't a collision that generates momentum that it's, no, we're only looking at the electrical forces. So that didn't work. And after this, we'll leave. But let's say I do this. If I do this, it's gonna go upwards, but what happens if I put a negative charge here? Oh, it started to bend.
That's possible.
It- Started to bend. Let's see if I put another negative charge here. Let's put a negative charge here. Let's put another negative charge here, and let's put another positive. But I don't want it to be so strong, so I'm putting it farther away. Let's do that. Let's see what happens there. Oh, but that didn't help. But is it clear that depending on where I put the charges, I'm gonna, the other charge is gonna be trying to move because the electrical fields are gonna be interrupted.
And if we get to the goal, we get the bonus points.
No, no, no. You need to get to the goal. You need to show me that you got to the goal.
Okay.
The bonus points are, there's 3 houses. The bonus points are gonna go in this order. The house that uses the least amount of charges is gonna get the highest bonus point. And then,
And we just take a screenshot of. what we-
no, I want you to, I want you to film the video of the,
Oh,
they'll film or you can do it with your cell phone or whatever. Right now, I put 2 charges. There's been a few teams that have put about 20 charges and the charges like,
Yeah.
and that's kind of cheating. The idea is to use the least amount
that's
of
how-
charges to make it get to the goal. The house that uses the least amount of charges is gonna get X amount of bonus points. Then the next house is gonna get, so it's gonna be first place, second place, and third place.
Do you remember which one's the one that had the least last year?
I don't remember, last year I didn't do the bonus that way. I think I just gave it to one house that had the least, but this time everybody's gonna get points. I don't remember how many charges they put. I have it written down somewhere. But there's an infinite number of combinations.
Yeah.
Actually, the trick isn't the amount of charges, is where you place them to do the sort of attraction. We're gonna talk a little bit more about this next week, don't worry. And I'm gonna let you know when it is. I'm just leaving you with this sort of mental gun. I'm gonna stop sharing now. And let's see, Ricardo, you had a question. Go ahead.
Oh, it was just about the bonus. It was just where do we send the video, through WhatsApp or is there going to be an activity?
I already activated, there's a discussion forum. So if you already want to do it, you can do it. It's the discussion forum is already activated. I haven't put a due date for that, but I think that probably, let's say that next Friday, we're gonna see what happens next Friday. So do it before 11 a.m. of next Friday. It's a mandatory activity for all houses. So all houses need to do the exercise. But I'm gonna give I'm gonna give points depending on how many charges you use, okay?
Okay.
And there's a discussion forum and just upload the video. My suggestion is you can film it and then put it to YouTube and just add the YouTube link. That would be easier than instead of uploading the video. Okay. And